Good afternoon, everyone. Our topic today is scene separation and data selection, or otherwise known as 2SDS. It is a temporal segmentation algorithm used in real-time video stream analysis. So this is a quick peek about what we're going to talk about today, and let's start by introduction. So there's two parts in introduction. First, we like to introduce the problem that includes the background and what we want to achieve. And the second part, we're going to talk about our motivation, more specifically to tell about why don't we want to use a neural network. Okay, just a quick remark here. So our focus today is going to be on the scene separation part of the algorithm, or otherwise known as temporal segmentation, which is a problem where we want to separate a video stream into different scenes. And by definition, a scene is defined as a group of similar looking frames that are temporally adjacent to each other. So in other words, a scene is the pictures in a video that is near each other and they look similar. The background of our problem is real-time video stream interpretation, and the important part is real-time. And this type of question include video semantics, video accessibility, and surveillance footage auto-interpretation, and so on. So the difficulty here is that traditional algorithms usually do not see video as a continuous stream of images, but as discrete frames. So this brings up a lot of problems because if we want to do a video stream interpretation, we usually want the algorithm to know the relationship between one frame and another. So if the algorithm doesn't see the video as a continuous stream of images, there is a very significant information loss here. So, moving on to the traditional approach, which is actually using a 3D CNN to do a video stream interpretation. And 3D CNNs are essentially CNN models with the additional temporal dimension. And what is missing with this type of algorithm is that 3D CNNs usually are harder to control when the video stream is very long, like an hour or two, or the video is of indefinite length, like a live stream. So an example of this would be that usually the longer the video, the worse the temporal resolution is going to get for the 3D CNNs. So it would be very hard for 3D CNNs to pick up very sudden or quick moves in a very long video. So to make a further comparison, it would be like trying to pinpoint a very small object in a very big picture using 2D CNNs. So after talking about the challenges we face, let's move on to our motivation. So when you think about it, you'll probably say that RNNs are really handy when it comes to handling temporal information. So why don't we want to use a neural network here? Why don't we want to use an RNN or a CNN? So the first reason for that is actually neural networks are relatively slow. So bear in mind that what we are trying to achieve here is a real-time video analysis. So the response time of algorithms is incredibly important to us. So the inference time of a lot of neural networks makes them very difficult to be used in real-time video analysis situations. And what we did is that we have made this very quick comparison of inference speed between two algorithms. So if you look at the table down here, and we have two algorithms here. The first one is the YOLO V5S, which is a very small and light CNN model. And the second model is our 2SDS algorithm. So if you see the data here, so you can find that the 2SDS algorithm is actually a lot quicker than ULV5S under the same hardware. So we have measured 227 frames per second at using the Apple M1 CPU. So comparing to the 11 FPS of ULV5S, the 2SDS algorithm is a lot quicker. And the second reason that we don't want to use a neural network is that we find that the 2SDS algorithm is actually fully capable of handling simple scene separation tasks. So these are the two reasons that we don't want to use a neural network. So moving on, we'll be diving into the methods behind the 2SDS algorithm. So firstly, we would like to begin with a quick comparison between a related work and our work. So the related work that we refer here is the slow fast network architecture. So the slow fast network architecture actually features two pathways. So the first pathway is the slow pathway, and the second one is the fast pathway. So essentially, the slow pathway is a CNN model with a high spatial resolution. So in other words, this type of CNN is very heavy, and usually it cares a lot about which objects are in this certain frame and what is the position of this object in this frame. So these CNNs are relatively heavy and they have a low FPS. So the fast pathway is also a CNN, but this type of CNN doesn't really care about which objects are in which frames. So they only know about the relationship between the different frames. And these type of CNNs are usually lighter than the slow pathway. So they have a much finer temporal resolution, or they have very high FPS. So by combining the slow pathway with the fast pathway, the slow fast network is going to get an architecture which has high spatial resolution and high temporal resolution. So this is essentially what we want when we do a video stream analysis. So we won't lose any information spatially or temporally. So moving on to our work, which is rather similar with the slow fast network architecture. So the difference here is that we replace the fast pathway in the slow fast network with the 2SDS algorithm. So essentially, we replaced a CNN model with the faster 2SDS algorithm. So our 2SDS architecture is going to have an even finer temporal resolution. What we want to talk about next is actually the methodologies behind the 2SDS. Essentially, the 2SDS is a two-step method. So the step one is scene separation, or otherwise known as temporal segmentation. And the second step is data selection. So our focus today is mainly going to be the scene separation part. So when you do a scene separation, the first step is usually downsample. So we have a 3000 by 3000 input image here in the figure 4, and we downsampled it to 8 by 9. So why do we want to do a downsample first? So the first reason for that is we want to simplify the calculation. So a 3000 by 3000 and RGB image is actually a ton of data, so it is not easy to calculate. So downsample it to 8 by 9 makes it a lot easier. And then the second reason that we want to do a downsample is that we want to make the algorithm less sensitive to small changes in the video. So what we mean by small changes is essentially it is still in the same scene, but we don't want this little movement to affect the algorithm's judgment whether it is the same thing or not. So doing this downsample, of course, we lose a ton of details in the image, but the upside is that during this process, we make the algorithm less sensitive. So the second step of scene separation is a grayscale image conversion. So we want to convert the previously 8 by 9 RGB image into a grayscale image. So this is actually pretty simple and straightforward. It is also to reduce the calculation complexity. So the third step of scene separation is to calculate the hash value. This is where it gets a little bit complicated. So previously we have acquired an 8 by 9 grayscale image. So what we want to do here is to convert this grayscale graph into a 16-bit hash value. So the rules are as follows. The first rule is that one binary value stands for the grayscale difference between the two adjacent pixels. So I'll give you an example here. So if you look at figure 5, so you can see that the first line here is 0 0 1 1 1 0 1 0. So this is a binary sequence. And how do we determine this binary sequence? Is using the rule B. So if the grayscale value of the pixel on the left is greater than the pixel on the right, so the value is 1, otherwise it is 0. So we'll give you a further example. So if you can see the two pixels here, they are nearly identical. So we believe that so the value should be 0. And you look at these two pixels. So the pixel on the left is actually lighter than the pixel on the right. So the value is also 0. And when you look at these two, so the pixel on the left is actually darker, and so the value here is 1. And essentially we have 9 pixels in a row, so we have an 8-bit long binary sequence. So the entire image will be converted into 8 times 8, that is 64-bit binary sequence, and we convert the binary sequence into a 16-bit hash value. So this is the conversion from the grayscale graph to the 16-bit hash value. And the last step of scene separation is to calculate the Hamming distance. So the Hamming distance is essentially what determines the similarity between two frames. So we have introduced before that one frame will be downsampled to an 8 by 9 grayscale image, and the grayscale image will become a 16-bit hash value. So every image is going to get its own unique hash value. So by calculating the Hamming distance between these two hash values, we get a general idea how similar are the two frames. So the smaller the Hamming distance, usually the two frames are similar. So the higher the distance, they are most likely to not be in the same scene. So to give you an example here, so we have two hash value h1 and h2. So calculating the Hamming distance is actually relatively easy. We only need to do an exclusive OR operation on the two hash values. So in the example here, the Hamming distance between hash value h1 and hash value h2 is 7. So this is simply acquired by doing an exclusive OR operation on these two hash values. So these are the 4 steps involved in scene separation. And to give you a general idea about the effect of the whole separation, so let me give you an example. So if you can look at the diagram here, it is actually very straightforward, right? We divide an entire video on the time span, and we have separate them into scene 1, scene 2, scene 3, all the way to scene n. So everything in scene 1, for example, involves very little movement, and the character stays relatively stationary in this specific scene. And it is also the same with scene 2 and scene 3. So this example gives you a general idea about how the scene separation works and what is the final effect of this step. So the idea is by doing this scene separation, and we combine this with the CNN output, we are going to have a very specific video semantics interpretation. And so, for example, like in scene 1, so we see Kirk and his crew on the bridge of the Enterprise. So this is what we get out of scene 1. And out of scene 2, we can also give a very specific semantic interpretation, and it is also the same with scene 3, scene 4, and scene N. So in general, this is how we combine the two SDS with another CNN model. Together, we combine it into the two SDS architecture, and this architecture is able to give a very specific semantic interpretation on every scene. So now our algorithm knows what happens in this particular video, what is the line of the story, right? So this is generally what we have achieved through combining the two SDS with a CNN model. So the second part of the 2SDS algorithm is of course the data selection part, and since this is not our main focus today, we're going to talk very quickly here, and we'll go through these steps. So the first step of data selection is the data smoothing procedure, which essentially is that we used a weighted average pooling filter to filter out all the data noise. So this gives us better data, cleaner data. And the second step is the data selection procedure. Essentially, we merge the selected frames into a single frame and use this as the output. So the final output of this particular scene is represented by a single frame in this scene. So next we'll talk about the experiment, and because we have only limited time and resources, we only did some preliminary experiments with our algorithm, and we used the YOLO v5 as the corresponding CNN in the 2SDS architecture, and we have chosen 3 types of testing videos. So the first one is interview, which are relatively stationary and they are very direct and clear. So this type of video, we think it should have the highest accuracy on our algorithm. And the second type is vibrant, which is the videos with a lot of movement and camera shifts. And we think that this type might hurt our algorithm because the 2SDS algorithm have been having a little bit difficulty when dealing with very fast movement. And the third type is hybrid. So this essentially is somewhere between the interview and vibrant videos. It is sometimes stationary and it is sometimes moving. So these are the preliminary results that we get from our experiment. As you can see in the table here, the interview videos have a very high accuracy. It have an average accuracy of 90.1%, and it has a 181 FPS. And the vibrant videos, it is where it hurts a little bit because the accuracy is only 54.9%, and we have an FPS count of 202. And the hybrid video have very high accuracy, actually at 99.06%, and a very decent FPS as well, 213. And of course, all the FPS data are taken on the same hardware sets that we used prior. So for the last part, we're going to discuss some future improvements that we can make on the 2SDS algorithm. And so the first thing that comes in mind is that we can introduce graphs. So if we can model the video frames using graphs, then we can dramatically improve the performance of the algorithm in fast moving scenes. Um, for example, in Figure 6, we can see some people doing sports, and usually these things move very quickly. But as humans, we also consider them to be in the same scene. Like even if the person with the bat hits the ball, it is still the same thing. But if this kind of dramatic movements is fit to the 2SD algorithm, it might think that these are two different things because the man moved quite a lot. But as humans, we can consider it as the same thing. So by modeling the video frame using graphs, we can essentially create an object tracking system that lets the algorithm know that the person is just moving a little bit, so the scene stays the same. So this is mainly the future improvements that we can have on the 2SDS algorithm. So to conclude what we have talked about today, we have some few upsides for our algorithm, which is that we have created and refined architecture compared with slow fast networks. This essentially gives us better temporal resolution and less key flops involved, so less computing involved. And the second one is that we have a very high FPS count, and we have reached decent accuracy on interview and hybrid videos. So these are things that we think the 2SDS has achieved, and there are also some problems with it currently. So it is currently less accurate on vibrant videos. And what we want to do in the future is to add a graph modeling system to improve the vibrant video performance of the algorithm. And also, some of the data needs further testing and to determine the exact performance of the 2SDS algorithm. So this is all for today. Thank you everyone for your attention.